Hi, good afternoon. Welcome to Maths this week, and going to go through two problems today about probability. Of course, the coursework has started. I put that out yesterday on Blackboard. So if you've not taken a look, take a look. The deadline is a week today, 3 o'clock in the afternoon next Tuesday. It's a Blackboard, it's an Excel based problem. So there's an Excel file, you download it, and there are two worksheets on it. On each worksheet there's a question, one from Dr. Abdul, one from me. And please use the worksheet to record your answers on and to show your working and explain what you're doing. Save it, upload it back to Blackboard through the Turnitin portal, and then we can access that spreadsheet. When you upload it, you will see that Turnitin kind of turns it into a page view thing, which doesn't show your work very well. But don't worry about that. We can actually get the Excel file, and we'll use the Excel file to mark the work. So don't worry about what Turnitin does to the way it looks. So we're talking about probability this week, and I think much of the stuff in the mini lectures will be familiar to you from previous years, from A-levels or before or elsewhere. I wanted to show you something before I move on, just to give you a kind of reason why we present it like this. So I need to share this screen. There we go. So here's some beautiful detail of some flowers, which I saw many years ago when I was a PhD student visiting a friend in a museum at Harvard University. And they're beautiful specimens, and remarkably, they are all made out of glass. 100 years ago, a father and son spent their lifetime's work making these beautiful exhibits, specimens of different plants and flowers, so that they can be displayed in a museum. And one of the things that impressed me about the exhibition and the work was the tools that they used to make it. This is a reconstruction of their workshop, and they could create the most delicate and the most beautiful and intricate objects out of glass using the simplest tools, basic pliers, a Bunsen burner, and glass blowing techniques. And some years, the students on the maths course are concerned that some of the maths we're teaching is too familiar to them. It's too similar to what they've learned before, and they want to be on to some harder maths, some new maths, something different. And I welcome that enthusiasm to explore maths and to do more maths. But there's also the reality that maths is a tool, and the better that you can use your tool, the more you can do with it, and the better the things you can do. And you can do great things with really simple tools. So the probability that we have, we really want to understand how to use it and what we can do with it before you'll do more exotic and different maths in other years. And of course, not everyone's seen the maths that you might have seen. So we need to make sure everyone's seen it, and to try and deepen your understanding of it and deepen your ability to apply it to different situations. So today we've got two problems which you've not seen before, which I'm going to talk you through. And this will address some of the questions about probability that we've seen in the mini lectures over the last week. And the objective is to use the simple rules of probability to do something useful in an engineering sense with them. The overall scheme of our lectures so far, we started by looking at an experiment. We saw that we can construct relative frequency density distributions from that. And we recognize that these are things that you can use to calculate the likelihood of things happening, or the likelihood of a material being a certain strength. That's from the experimental side. Once you have some information about your system or about your material, you can use probability theory to then work out what's likely to happen in a different scenario, in different scenarios, what's likely to happen in the future. And then you can make judgments and decisions based on that. So we've got two examples today, which will help us to make some judgments about whether how a system will perform in the future and whether that's acceptable to what we need it to do. So the first one here, I've got it in Excel just because it's not clear when I printed it out on my piece of paper. So I'm just going to read the question and then work through it on the piece of paper. And it has a case that a thermostat will fail, and it will fail with a probability of 0.3 if component 1 fails, and it will fail with a probability of 0.7 if only component 2 fails. So it's got two components in this thermostat. Both of them could fail. If only component 1 fails, then the thermostat may fail with probability 0.3. If only component 2 fails, the thermostat may fail with probability 0.7. Now, if neither fails, the thermostat definitely won't fail. And if both fail, the thermostat definitely will fail. So it has probability 1. Let A be the event that component 1 fails, and B be the event that component 2 fails, and C be the event that the thermostat fails. So first of all, we're using the terminology that we learned in the first mini lecture about events and outcomes and so on, so that we can categorize this problem or write this problem in terms of a probability problem. And then we want to work out two different scenarios, A and B. The first one is, what's the likelihood, what's the probability of a thermostat failure if events A and B are independent and they both have the same probability of 0.1. So the probability of component A failing, sorry, if component 1 failing is 0.1, and the probability of component 2 failing is also 0.1, and they're both independent. So that's the problem that we've got, we want to work out. And we have the tools to do that now. So this will enable us to work out the system behavior from the individual components behavior. So I'll go back to the sheet of paper. Just checking on the chat. I can see lots of questions about the coursework. So I will check through those questions at the end and catch up on that. So coming to our problem, just going to rewrite the key aspects of it so that we can all see that clearly. So we've got an event. There we go. Event A, and that is that component 1 fails. And we've got event B, and that's that component 2 fails. And the question's giving us the probability of these for the first case. The probability of either of those failing is 0.1. And this will be over a given period of time. And the other event is C, and that's that the thermostat fails. We can call that probability of C, but we don't know what that is, and that's really what we want to know. We've got a device, we know something about the components of it, but we want to know how the overall device is going to behave most likely in the future. But we're given a bit more information than that. We're also told that the probability that the thermostat fails is 0.3 if only component 1 fails. So how can we write that in our probability terminology? So the probability that the thermostat will fail, so if the thermostat fails, that's event C, given that only component 1 fails. So given that only component 1 fails. So only component 1 fails means that A happens, that's event A, that component 1 fails. And also the intersection of that with the complement of B. So component 1 has failed, but component 2 has not failed, because it says if only component 1 fails. So we can write it like this. So we've got the complement there that we've met as well. And we were told that that's equal to 0.7. And then the other one was the probability of the thermostat failing if only component 2 fails. So that means that we have the complement of A and B, and that's equal to Sorry, I think I've made a mistake. That's not 0.7. That's 0.3, and that's 0.7. If only component 2 fails. Yep. And of course, there's a couple of other scenarios that could happen that we're given the probabilities for. So the probability of the thermostat failing if neither fails, so if A doesn't fail and B doesn't fail, then it's equal to 0. And we're told the probability of the thermostat failing if both of them fail is equal to 1. So that's the information given to us in the question. So we want to use our rules of probability to work out what this is PC. Okay, so the first thing I'm going to do is just going to map out the possible scenarios that could occur in this system, just so that we can be clear about all of the possible eventualities. So if we take the first event, that either one fails or doesn't fail, and for each of those cases, we have the possible events that component 2 fails or component 2 doesn't fail. And then for each of those, we've got the third possible outcome, which is that the overall thermostat fails, C, or that the overall thermostat doesn't fail. So we can see there are 8 possible scenarios in this problem. And for each of these, we could call this overall event that we have A and B and C, we could just call that C1 for convenience. Probability C1 is going to be the probability that we have A happening, and the probability that we have B happening, and the probability that we have C happening. So that's one way in which the thermostat could fail. And then there are 4 ways it can fail. We have this way, A and not B and C. We have the probability, the third one, probability that A didn't fail, but B did fail and C fails. And then fourthly, the probability that A didn't fail, B didn't fail, and C does fail. So those are 4 different possibilities. And we want to work out what the total of all that is. What's the overall probability that the thermostat will fail? So we can look at these, and each of these outcomes is mutually exclusive. They're mutually exclusive. It's not possible to have that happening and that happening, or any other combination. And when you have something that's mutually exclusive, then the probability C that the thermostat fails is going to be equal to the probability of C1 plus the probability of C2 plus the probability of C3 plus the probability of C4. So that's one of the theorems we've got from our mini lectures. Sorry, it's not very focused. I can't seem to improve that. But that's probably C1, C2, C3, and C4 added together. So we're getting a structure now where we can start to imagine how we can work out what the overall probability of failure is. Next, we're going to use another theorem. from the mini lectures, the multiplication theorem, which tells us that the probability of A and B is equal to the probability of A multiplied by the probability of B given A. And that's going to help us to work out what some of these are. So we've got each of these four terms here, the probability of A and B and C and so on. And we need to add these up. That's the first thing we learned because we saw they're mutually exclusive. We need to add each of those up. And then we need to find an expression for each of those in terms of things that we know already. So we don't know what this is, but we can see with this rule, we can split up something where we have an A and B into two parts. And we can see we've got lots of expressions that are in terms of the probability of C given something. So it makes us think, well, if we can turn this into the probability of C given something, then we'll be able to use the information we have. So we want to use this type of expression, but the term here, B, is going to be our C here. So for example, we can take the first case, the probability of C1, which is the probability of A and B and C. What we're going to do is imagine we've got another bracket there, so that's A and B and C. And so then we can use that rule to write it like this. The probability of A and B multiplied by the probability of C given A and B. Somebody asks, why is it this? Well, look to the mini lecture for that because we went through the theorems of probability and where we talked about these rules. Once we've got this, can we make progress with it? So P of C given A and B, that's the sort of thing we've got up here. There we go, we've got that one, P of C given A and B. And here we've got the probability of A and B. We don't know that yet, but we know the probability of A and the probability of B separately. And in this case, we know that they were independent. And so we can use another result. For independent events, the probability of A and B is equal to the product of the two. And so that means that we can find our probability of A and B because we know PA and we know PB. So for this case, I write it out in full. The probability of C, the probability of failure of our thermostat, is all of these four terms added together. And then for each of them, we can manipulate it with the multiplication theorem, and then we can use our independent events result as well. So then this is going to work out as probability of C given A and B, PA, PB, plus C given A, B complement, probability of A, probability of B complement, plus the probability of C given A complement and B, PA complement, PB, and finally probability of C given A complement and B complement, PA complement, B complement. So we've got those four terms and we've made our substitutions in for each of them. And now this is entirely things that we know the values of. So here we've got probability of failure if A and B happens, that's this term here, that's equal to 1 times the probability of each of those is 0.1 plus probability of failure if A and not B, A and not B is 0.3 times 0.1. Probability of B complement, well, that's another result that we're using. The probability of B complement is equal to 1 minus the probability of B. And so that must be equal to 0.9. Probability of C given A and, sorry, not A and B, that's 0.7. 0.9 times 0.1. And then the final term, if neither A nor B fails, then C won't happen. So the thermostat won't fail, so that's 0. And then you can add those up. And we get the overall probability is 0.1. So I've worked through it systematically here. So you can see the different steps that we've made, the different assumptions we've made, each point in the different theorems we're using to get there. I'll just write down the last theorem. The last theorem that we used was that probability of A complement is 1 minus the probability of A. That's the last one we used. And that enables us to solve our problem there. So I'm just looking at the questions on the chat. So why is it PA? If I put those there, you can see them. Why is it PA multiplied by P B given A? Well, that was in the mini lecture, so that's done. Seems more complicated than the mini lectures. Well, I'm working it out step by step. So if you're doing it yourself, you might take some shortcuts to get there faster. Are PAC and PBC independent if PA and PB are independent? Yes, that would be true. Yes, that's right. Great, thank you. And thanks for the comments that other people have made in there. That's the first case. And then our second case is a little different. That was the case where A and B are independent. Our second case, what's the probability of thermostat failure if, I'll write them out a bit bigger so we can see them. Probability of A is still 0.1. The probability of B given not A, so if A doesn't fail, the probability that B fails is 0.1, but they're not independent anymore. So now if A does fail, that changes the probability of B failing. So now if A does fail, the probability of B failing is now 0.9. So now they're very dependent on each other. If A fails, it's likely that B is going to fail as well. So that's a different scenario. So looking at our solution from last time, we need to check where does that change in the assumptions affect our analysis. It doesn't change this point, and it doesn't change this point. The point it changes is here when we're trying to find what our term probability of A and B is. Here we use the result, which is requiring them to be independent, but that's not true anymore. So we've got the same analysis up to that point, but now we need to consider our probabilities when they're not independent. So the probability of A and B when they're not independent is the probability of A multiplied by the probability of A. Sorry. multiplied by the probability of B given A. So that's the same we had before, the multiplication theorem. So do we have enough information to work the 4 cases out that we have? So we've got complement of A and B, A and B complement, and then we've got A complement and B complement. So we've got those 4 cases that we're going to need to work out. So for each of those, we can write out the equivalent So we've got those 4 things we need to find. So what do we have? Well, we've got a couple of these. We've got PA, and so therefore probability of the complement of A is 0.9, so that deals with one of them. The probability of B given A complement, great, but we need the probability of B complement as well given A and A complement. So again, we can find that out easily. The probability of B complement given A complement, that must be equal to 1 minus this term. So that's going to be equal to 0.9. And the probability of B complement given A, again, that's going to be equal to 1 minus this term. So that'll be equal to 0.1. And so now we've got all the things we need to work out each of these terms. So this one's going to be 0.1 times B given A, which is 0.9. This one's going to be A complement, which is 0.9 times B given A complement. B given A complement was 0.1. That's 0.1 times B complement given A. B complement given A is 0.1. It's 0.9 times B complement given A and A complement is 0.9. And so we get those 4 values now for the different multiplication terms. And so again, now we could use that same expression that we had before, like so. So we've got the same expression, but now instead of the PA, PBs, we're going to have these terms here with these values in. And if you work through those, you'll find the solution. I will leave that to you to finish if you want to do it, but you can see the principle of how you do that. Somebody asks, is that a typical exam question? Is that a typical exam question? Yeah, it could be. That's the sort of thing we expect you to be able to do. How do we know if they're independent or not? Well, that's a good question. So in an exam or something like that, we will tell you if they're independent or not, or we'll give you a description of a system and we'll ask you to work out, that will be the challenge, the question for you, to work out whether they're independent or not. In real life, you have to come to your own decision about that. No one will necessarily tell you the answer. And you'll have to think about it. In this case, you've got a thermostat with 2 components in it, which might fail, might not fail. If those components come from different suppliers and are produced independently from each other, you might say, okay, they're likely to be independent of each other, whether or not they fail. But then perhaps the mode of failure is caused by the thermostat overheating. And if it's the case that if both of those tend to get too hot, they tend to fail, then that might actually mean that there is a common cause of failure, and that means that they're not actually independent. And so whether they're independent or not makes a big difference to the analysis of a probability problem, and you have to be careful. that the mode of failures aren't down to common causes, which can make things which might have been made independently, but they could still fail in a dependent way. Do we use the same theorem for adding dependent probabilities? I'm not exactly sure what you mean by that. If you want to post that on the Blackboard discussion board and explain what you mean, then I will answer it there. Okay, so didn't want to do that. Minimize that. So the next one is a different problem. Share my screen. There you go. So question 2. So this is another example of how to use our knowledge of probability rules to analyze a system and find out something useful about it. So here we've got a flow sheet that shows a process. I think you can see all of that. Yep. So the process flow sheet below shows a heater, R1, there we go, followed by 2 pumps in parallel, R2 and R3, and a subsystem of 5 turbines, R4, R5, R6, and R7, and R8. The 2 pumps work in parallel, and so this pump subsystem, the subsystem of the 2 pumps in parallel, we can say that that will work if at least one of the pumps operates. So the overall process will cope if one of those fails. As long as one operates, it will work. And likewise for the turbines, well, it can cope as long as at least 3 turbines are operating. So you can have a couple of failures in there, you can have 3 failures in there, but it would still work as long as 3 are left working. And these 3 systems, the heater, the pump, and the turbine subsystems, are connected in series, so they must all work properly for the whole system to work. And we're given here some probabilities between 2 scheduled maintenances. Each component may fail independently of the others with these probabilities. So we've got a probability for each component failing. And obviously, we're going to try and work out some things about this. We're defining the reliability of the system. So the reliability of the system is when one of its subsystems does not fail between scheduled maintenances. So if any one of the subsystems fails, if this part fails, or this overall part fails, or this overall part fails, if any one of those fails in series, obviously the whole system won't work. So the reliability is the probability that none of the subsystems fail between 2 maintenances. So we've got an event, Wi is the event that component I is working properly. So first of all, we've got a question of what's the reliability of the heater, what's the reliability of the pump subsystem, and then thirdly, what's the reliability of the turbine subsystem. And it gives some suggestion of how to do that by taking the spreadsheet and using a spreadsheet to find all the possible combinations of events, sort of outcomes for each turbine, and the probability for each, and then calculating the probabilities of each of those possible events. And then with that, we can calculate the overall reliability of the system. And then finally, we'll take a look and just consider whether the system is designed the right way and what the options are for reducing the number of components and how that would affect it. Okay, I can just see there's a thing on the chat. Where are these Excel questions? They're on my computer at the moment. They're not anywhere else. I just made them for our class today. So I can put them online afterwards so that you can take a look at them more closely and look at how we've done it. We've got the solution to question 1. Not on that one, so it's on my other spreadsheet. The solution to question 1 is on this spreadsheet as well. So you can look at that one when I put it online. So we're going to talk through question 2. I'm just going to show you the solution as I made it in Excel. Let's try and move that out of the way. Again, this is just to show how you can combine the rules and start to analyze relatively complicated things and find out useful stuff about them based on some simple rules. So the first question is, what's the reliability of the heater? That's the easiest one. The heater is unit R1. The probability of it failing is 0.05. And so the reliability of it is the probability it doesn't fail. And so that's the complement of this term. And so it's 1 minus that. And that's equal to 0.95. What's the reliability of the pump subsystem? So the pump has 2 pumps. If either of them fails, it's okay because one of them still works. So it requires both of them to fail for the system to fail. And so the reliability is 1 minus the probability of failure. And so failure occurs when both pumps fail. So that's when we have the complement of R2 and that should be the complement of R1. Well, we have the complement of R1 and the complement of R2. So that fails and that fails. So the probability of R1 failing, sorry, R2, apologies, it should be R2 and R3, do it wrong again. R2 and R3, that's it. So the probability of R2 failing is 0.1, R3 failing is 0.08. So here we've got 1 minus those two terms, 0.1 times 0.08. And that gives us the reliability of the pump subsystem. So that's good, got 2 parts of it done. Then the third one is expand and complete the table to show the turbine subsystem using all permutations by which at least 3 turbines are working. So we talked about permutations in our lectures as well. And we can work through these systematically in Excel without too much trouble. We've got these 5 turbines, R4 to R8. So obviously the first case we can say they're all working. Then we can say one's failed, and then we can rotate that, cycle that failure through the whole system. Now we say 2 have failed, and then we can cycle the second failure through the system. And then 2 have failed, starting with these 2. We can cycle the failure through the system, and so on. And then that's the last one there. So that's where 2 have failed. And we have 3 working still. So if any more fail than that, then the system doesn't work. So this contains all of the permutations that leave the system working, because all of these have at least 3 working turbines. Now, we can then find the probability of each of these events. So for R4, it's either 0.8 probability of it not failing, 0.2 probability it does fail. And so you can put in the corresponding probability for each of these outcomes here. And you can see in Excel, I did this using, you can do it manually if you want to. In Excel, I did it using an if command. Expand that. So this is just to save a little bit of finger work on the keyboard. So if B45, that's that cell here. So if that's equal to W, then we put in 1 minus the probability of failure. Otherwise, if that is equal to WC, the complement of W, then we put in the probability of failure, J13, which is from the cells above. And then this term here at the end, so if it's not that and it's not that, then this is just providing an argument for what to put if neither of those things are true. One or other of those things must be true, so we should never get that outcome. And the inverted commas just means we're putting in an empty cell. So we've done that. And when we've done that, we can just copy those across the whole table, which I'll illustrate again. So you can copy those and it fills the table with the appropriate values. So that can just make it a little simpler when you're using Excel and you can analyze a bigger system. So then the probability of each subsystem event, the probability of R4 and R5 and R6 and R7 and R8 doing all of these different permutations. But we were told they're independent, so whether R4 fails is independent of whether R5 fails. So these can be multiplied together like this, P, R4, P, R5, P, R6, and so on. So then we can just take each of these probabilities we've identified and product them. So we've got the product of those 5 terms for each of those. Each of those is mutually exclusive. It's not possible to get 2 of these things happening at the same time. So that then when we find the probability of the overall turbine subsystem working, it's the probability of this one, or this one, or this one, or this one, or this one. When they're mutually exclusive, we can add them together. So we've just added together that whole column of numbers, and that gives us another subsystem probability of reliability, 0.733. Okay, so using that, we want to find the system overall reliability. So that means that all three things need to work. The heater subsystem has to work, and the pump subsystem has to work, and the turbine subsystem have to work. They all have to work because they're in series. They're independent again. We were told that they're all independent. So again, we can multiply the independent subsystem probabilities together to get the overall system reliability. And we get 0.917. So that's very nice. We've been able to calculate an overall system reliability based on the individual components and their reliability. So that's useful. That gives us something useful. But we've not made any decisions yet. So the last question is nice because it gives us a chance to make a decision about how we should design this. So it just takes a scenario that says turbines are expensive. We've got 5 of them, and we've been told that we only need 3 to work for the system to be okay. So it begs the question, there are financial incentives to remove one of them or to build it in the first place without one of them. So is that worthwhile? So for example, if you remove turbine R4, that's the least reliable one. Let's just check that. So here are our turbines. Yep, R4 is probability it will fail is 0.2, all the other ones are below that. So that's the least reliable turbine. So why don't we take that out, save the cost of buying it and maintaining it and everything? How will that affect the reliability of the whole system? So based on that, we've taken R4 out, and we can repeat the process where we have the permutations again. Now there are only 4 turbines, so there's fewer permutations to work through. 3 need to work still, so we can only afford 1 of these not working. Again, we get the probabilities of each of those event outcomes, probability of the event, probability of the reliability of the whole subsystem, and then we calculate again the probability of the whole system by multiplying them in together individually. And now we see it's 0.852, and so we've got a reduction from the original reliability of 0.917. Now it's 0.852, so it's a reduction of 7.1% in reliability. And this is enough information then to come to a judgment of whether or not you think this is a worthwhile thing to do. You'd have to then factor in the cost of downtime. So if you had an unexpected shutdown of the plant, you'd have an idea of how much that will cost you per day. And so you can use this change in likelihood of a shutdown, calculate the likely cost of additional shutdown due to the change of removing R4, and then compare that to the money saved by taking R4 out. And whichever is financially better, then that might be what you choose to do. Okay, so that's the end of the examples. Thank you for listening. Just check the chat. So where are these Excel questions? I'm going to add them and the solutions to Blackboard after this so that you can take a look at them. I'll upload them along with the recording of this class. In regards to the assignment, okay, what's the difference between independent and mutually exclusive events? Okay, what's the difference between them? They are different things. So 2 events are independent if the probability of one occurring is not affected by whether or not the other one has occurred. But it's possible for both to happen at the same time. A mutually exclusive event is 2 things which can't happen at the same time. So for example, if I toss 2 coins, they are independent because the result from one coin that I've tossed will be independent from the result of the other coin that I've tossed. But it is possible to toss them and get ahead on each of them. So you get the same outcome on each of them, but that outcome has been arrived at independently. for a single coin toss, it's not possible to have a head and a tail at the same time. It has to be one or the other. So for a single coin toss, heads and tails, the possible outcomes, they're mutually exclusive because it's not possible to have both at the same time. And I see someone's answered that as well in the chat, so thank you very much. There are questions about the assignment. Some of them have been sent to me privately. And what I'm going to say, all the questions about the assignment, please put them on the discussion board forum. So if I'm answering questions about it, first thing to say is I can't answer any question that is about how do I do this question, obviously, because it's an assessed piece of work. So we've set it for you, and the challenge is to work out how to do it and deliver your solutions. I can answer questions if you think it's unclear. I can, Dr. Abdul and I can clarify any misunderstanding like that. But you should put it on the discussion board because everyone gets a chance to look at it the same way. So please put any questions about the assignment onto the discussion forum, and you'll see that there are a few already. Dr. Abdul or I will answer them promptly, and then you can get your answer there, but then everyone can see it and everyone can get the same information. So please do that if you've got those questions. Thank you very much. I'm going to wrap up there. The TAs are ready and waiting for you in their sessions. If you were with Pia, then he's not available today. So then you're going to need to join one of the other sessions, please, this time. So what I'm going to do is just get the Zoom details for the other sessions and put them on the chat so that you can join one of them if you want to. Where are they? They're in Blackboard.